All right, so we're gonna start phase four officially today. Congratulations, everybody. Um, so I wanted to start with a quick overview of what phase four looks like. It's quite different from the last few phases, mainly because of what the project's going to be about. So to start, I think I'll start by explaining the project is going to be one of four main topics. Here you can see I've outlined the project topics are going to be time series, rec systems, image classification, or NLP. And so for your project, you're going to choose one of these. And it's up to you. There are provided data sets for each of these, but you're also free to pick your own. So same process, if you want to do your own data set, just let me know. But because these topics are all pretty different, most students treat this phase as an elective phase. I will say this is also a really good time to not like think about it seriously, but start thinking about what you want your capstone project to be. I know it's a lot happening all at once, but you can use this project in a way to either complement your capstone project in like having very different projects, or if you already sort of have an idea of what you want to do as your capstone, this phase four project can also work as a building block for your capstone. So I know it's a lot to think about, happy to discuss it during one-on-ones, but this is something that's good to keep in the back of your mind. I will say that most students, myself included, usually choose like two of these topics to focus on and then leave the other two for after graduation. But in terms of the labs, because you'll see there are a lot of labs for these, good to at least read through the first few labs of every one, just so you have an idea of the concepts, the underlying concepts that go behind each of these. But yes, focus on the one or two that you are most interested in or you think are going to be most relevant. And if you want help with picking, happy to talk about it at one-on-ones as well. So these being the main topics. Oh, was there a question?
Yes, are we going to have a pair work for phase four project or?
That's a good question. So it's going to depend because I will send out a survey um, at the start or midway of week 3. And then you'll indicate what project you want to work on. And really, it depends on how many people want to do the same project. If you're the only one that wants to do a specific project, you'll do a solo project. And if there are multiple people, I think this is definitely one that you want to do in groups, mainly because you only have 1 week for this project. And I know the last two projects, because of the timing of the phases, we did have 2 weeks, but this project is truly a 1 week project. So because of that, I'll be asking for like your first and second choices. Most of my students end up doing their first choice. The only reason they end up not doing their first choice is because they don't want to work alone. So yeah, there is a little bit of flexibility there, but you will need to tell me what you want to do your project on so I can pair you guys up. And then similarly, I'll be putting you all into working groups that will come later today. Any other questions before I like dive into the structure, a more in-depth structure of the phase? All right, so for this week, we're doing PCA and clustering to start. Today we'll do PCA, tomorrow we're doing clustering. These are the two unsupervised learning techniques. And these are very complementary and optional to the bigger topics we'll be covering this phase. So today and tomorrow's material are things that you may or may not use for a phase 4 project. Maybe you incorporate it into your capstone, but these are all optional. These are very complementary things. On Thursday, and I did see, Sarah, you had questions about PySpark. We're going to be talking about big data at a very, very high level. Once you go into the labs and install your Docker and everything like that, once you do that, it's actually just pandas, but slightly different syntax. It's basically working with pandas in big data. And so all of that syntax, I think following the labs is probably the best way to learn it. I will say very, very, very few students end up working in PySpark, but it's just good to know and good to have that experience. Setting it up is the hardest part. And unfortunately, I only really know how to set it up on a Mac computer. I will source instructions from other instructors before Thursday though, so not to worry about that. And then recommendation systems is on Friday. Recommendation systems is my all-time favorite topic. So I'm really, really excited to share that. And that will be like one of the first main electives of the phase. And if we take a look at the rest of it, the week after, next week, we'll be doing time series, NLP. I'm actually going to turn NLP into 2 sections because there's NLP here, which there's a lot, but I will put out what are the ones to focus on. There's NLP here, but there's also deep NLP that I do think is really important as well. So even though it's in the appendix, I'm going to be talking about some of that stuff too. And then after that will be a whole week of neural networks. The last topic here is operationalizing code with AWS. I'm going to tell you all now, this is not going to be a study group because literally if you click into this, they will link you to the Amazon tutorials, which are way better than I can explain. So this is not going to be a study group. This is often a topic that students don't look at until graduation. It's just good to have all the resources in one place. I understand that. But I'm not going to do a study group on that just because all the instructors Amazon has like videos explaining exactly what I also would explain, and all my information would come from that too. So just a heads up, there's not going to be a study group on the last topic. Any questions about like the overall structure? All right. Each of the things in the appendix, I would say like about half of it, I'm actually still going to talk about just because each of you for your projects are going to do more of like a deep dive into those electives. But yeah, yes, that's what I wanted to say. Okay, so let's get into PCA. Any questions regarding the whole of phase 4 before we get into it? All right. I think we actually have seen this slide deck a couple times because I know that last project, some people were interested in PCA, but I think good to just go over all of it again. So first topic of the phase, PCA, which stands for Principal Component Analysis. So quick agenda, we're going to go over the differences between supervised and unsupervised learning and what PCA is. We'll talk about why we even want to do PCA, how it works, and how we evaluate it. All right, so really quickly, the difference between unsupervised and supervised learning. The last 2 projects that we did, regression, classification, these are examples of supervised learning. It's done to predict on labeled data. I know different people think of it in a different way. I find that the most helpful way to think about when someone asks me, is this a supervised or unsupervised learning problem? I just think about, are there labeled data? Is the data labeled? Like all of you were predicting like churn, not churn. You're predicting the severity of car crashes, for example. In unsupervised learning, there are no labels. We'll be talking about clustering tomorrow, but I find that clustering is actually the easiest example to explain. So in clustering, a common example I give is for example, and I don't know why I always think about sports examples, but in basketball, there are the 5 main positions. I think that's what it is. And oftentimes, I think these positions were determined in the past or something. And a very, very common data science project is performing clustering to determine whether there are new groups of data. Like, is there a different, better way to group players based on maybe their statistics or based on the way they play, so on and so forth. So clustering is unsupervised because with these new groups that you're forming, all you're doing is telling the algorithm how many groups you want. So let's say with all of your players in, I don't know, basketball, you want to group them into like 3 main types of players. You can't even tell the algorithm, well, I want one group of tall players, one group of short players. You just tell them how many groups you want, and the algorithm will figure out the best, most optimal way to group them. And we'll be talking about that tomorrow. PCA, which we'll be talking about today, as another unsupervised learning method, and LDA, which I will talk about during NLP. LDA is actually very, very interesting because what LDA does is it does something similar to clustering on groups of text. And what LDA does is it actually extracts topics. So for example, if you're giving it, I don't know, every single New York Times article, LDA will be able to find like your salient topics, like for example, politics or like science or I literally can't think of another topic, I don't know, arts or something. So LDA, which is really, really cool, something I'll talk about when we get to NLP, which is also an unsupervised learning problem because you literally tell it how many topics you want it to look for. Questions so far? All right, so dimensionality reduction. PCA is a form of dimensionality reduction, as I think I've mentioned here and there. PCA is used to reduce the number of columns in your data frame. There are other forms of dimensionality reduction. One of them, which I will mention during a study group, during an office hours while we're working on projects. I think I mentioned it this past time as well, but doesn't matter. But PCA is a form of dimensionality reduction that it's unsupervised because we only tell it how many dimensions to reduce it to. So most common use case is, let's say you have a data set with like 1,000 rows, but 5,000 columns. Typically, you want to have more rows than columns. You could use something like PCA to reduce the number of columns that you have. So with your 5,000 columns and 1,000 rows, maybe you tell the algorithm, all right, I just want 100 columns, and it'll automatically reduce the dimensions of your data set. So the way that dimensionality reduction is done, PCA reduces the dimensionality of the feature set into whatever number you tell it, that number of principal components. So principal components is the name of each new column that is created. And the main thing it's optimizing for, so it does not really a gradient descent procedure, but it's actually a linear algebra procedure that we'll talk about in a little bit. It tries to maintain the variance of your data as much as possible. And maintaining the variance of data might be something that sounds a little abstract, but if you think back to when we were talking about linear regression, literally our R squared is how much of the variance is explained in our data by the model. And in a very similar way, PCA, you want to maintain the variance of your data as much as possible. And finally, something that's very important to remember is each principal component. So let's say you're lowering your dimensionality from 5,000 to 100. Each principal component is made up of a certain proportion of each original feature. So let's not do that 5,000 example. Let's just say we're doing from 10 features to 2 features. Each of the 2 new features is made up of some proportion of the 10 original features. So it could be like 0.1% of the first feature, half of the second feature, 1/3 of the third feature, so on and so forth. Linear combination. So very similar to like the formula that our linear regression looks like. Questions so far? All right. So why and when do we use PCA? A phrase that is used pretty commonly is the curse of dimensionality. So as we have more features, and features being the number of columns, data points become more sparse. One of the readings under PCA actually, I think, explains this pretty well. But basically imagine that if you were computing the distance between 2 points and you just had 2 dimensions, the distance between those 2 points is literally like that distance there. But if you have 2 points in like 3 dimensions, that distance would get a little bit longer if you think about it. And then if you increase the number of dimensions, the distance between points gets larger relative to fewer dimensions. And so that's the idea of how your data points become more and more sparse. Distance between the points gets greater, making it more difficult to implement some machine learning models. So you can imagine models like k-nearest neighbors that are distance-based. A lot of computation has to be done, right? You're calculating the distance between a point and every single other point. The more dimensions that you have, the more complex that distance calculation becomes. So it can really increase the complexity of your model. And with complexity, which is a good term to remember, some of you might have heard the term big O notation. Unfortunately, we don't talk about it formally in the course, but it will be something that I do talk about when we get to capstones. You have to think about time and space complexity. So with time complexity, as you know, similar to that KNN example I was just talking about, the more dimensions you have, the longer it's just going to take much longer to run, right? You have more dimensions to calculate the difference in your points, the difference between your points, so more time complexity, but also space complexity. So if you think about it, space complexity or memory complexity is when you're running certain models, sometimes a lot of data has to be saved. So if you have, for example, like let's see, what's a good example? let's say you have your gradient boosting model. Now with your gradient boosting model, you have to save every single subsequent tree of your model, because that's something that you can extract from your model after it's trained. And an example is, the more estimators you have in your boosting model, the more space it's going to take up. So that's also something to consider, especially as we work with more and more bigger data sets and also more complex models. So when to use PCA? You want to use PCA when you have a lot of continuous features. So unfortunately, PCA works better with continuous features, just because with continuous features, you have a better measure of the variance. If you have like categorical, like 0 and 1, you can still get a variance, but it's less descriptive. Not to say that you cannot perform PCA on categorical data, you still can, but the effects will be slightly different. And PCA is also really good for clustering or for very computationally heavy ML algos like SVM. I don't know how many of you tried to run an SVM for your data set for this past project, but I think for some people who had like over 100,000 rows, SVM would have taken a really long time, especially if you had like maybe like close to 100 columns. What some people do is you first do PCA on your data set so that you have fewer columns for your model to run computations on. I'm not sure if I have it in this slideshow, but another really good use for PCA is if you want to visualize your data. Because visualizations, and because we are human, we can only see 2D and 3D. If you want to visualize like your 10 column data, or it could be even more, your 1,000 column data set, if you want to visualize that, you can use PCA to narrow it down to 2 or 3 columns and plot it as like a scatter plot on a graph, for example. So if you want to do like a very abstract visualization of all of your data, you can use PCA as well. Questions so far?
I have a question.
Mm-hmm.
PCA only works on pair features. I mean, by using eigenvalues, we continue a feature in opposite way of eigenvector to make it 1.
I'm not sure what your question is asking. Can you repeat? Can you say that again?
In the reading materials, it says that actually it presented with 2 features, and these 2 features, by using eigenvalues, were opposite of each other, and they become 1 feature.
Kind of. Are you talking about creation of the principal components?
Yeah.
Okay. I'm going to explain it, I think, the next slide. So hopefully that clears things up. If not, happy to talk about it in more detail. Any other questions about any of this stuff, like when to use PCA, before we move on? All right. So PCA works by linear algebra methods. Remember how we solved linear regression, I think, at the very beginning of phase 3 using linear algebra? It's actually kind of similar. Mathematically, and for people who know linear algebra or have taken a linear algebra class before, principal components are found through doing eigendecomposition of the covariance matrix. Doing eigendecomposition is like a whole set of steps to basically take a matrix and factorize it in a way. So if you remember, I don't know if this will help many people, but for example, you have like your algebraic equation. If y'all remember x squared plus 2x plus 1, and I don't know, in like high school, you had to do this exercise where if you're given this quadratic equation, you can represent it as x plus 1 multiplied by x plus 1. So you're trying to represent like this quadratic equation as a product of 2 different linear equations. I don't know if that was helpful, but that process of factorizing, turning one equation into a product of 2, that's what eigendecomposition is sort of like. We're taking this covariance matrix, and the covariance matrix we actually know from our df.core, the correlation between each and every feature that we have. We're taking that matrix, that correlation matrix, and we're actually trying to separate it into a product of eigenvectors. If that doesn't make sense, it honestly doesn't really matter. I don't think any of my students have, at least no one has told me that they've been asked a PCA in-depth question in an interview. But it's basically linear algebra, and you're trying to do some decomposition. And decomposition, you're trying to break up your covariance matrix. So the steps of PCA, first of all, very important to recenter your data such that the means of each feature is 0. There's, I think, a mathematical explanation of why that's important in the stats quest video. And also, I think they talk about it a little bit in one of the readings. But you want your means to be 0. Means being 0, that means you have to use a scalar that will center your data at 0. So likely not min-max scalar, because min-max scalar, I always forget if it's -1 to 1 or 0 to 1, but your means will not always be at 0. So you likely want to use standard scalar for this. You will get your covariance matrix, your df.core, and then you want to get the eigenvectors of your covariance matrix, and your eigenvectors are figured out through this decomposition. And what do eigenvectors mean? This might sound a little bit abstract, but eigenvectors, and I did talk about in linear algebra, vectors could be like a linear equation. So eigenvectors of a matrix basically show you, oh, that's not a good I was going to say the span of the matrix, but that doesn't make sense to all of you. Basically, it'll be such that it looks for directions of your data that aren't correlated. So every vector is going to be 90 degrees to each other. If that doesn't make sense, it's okay. I'll send out, there are actually a couple good Medium articles that I'll send out after this. You're going to sort the eigenvectors and then multiply them by the recentered data. And so your principal components end up being, and that's how it ends up being, a linear combination of your original features, because each vector is going to be the length of your original features. Does anyone have any questions about that?
Eigenvectors are the number of features that we might end up having at the end?
So eigenvectors are, you can sort of think about so the length of each eigenvector, is going to be the same length as the number of features that you have. And then you actually don't use all of your eigenvectors. You only use the number of eigenvectors that the number of principal components that you want. So each principal component comes from an eigenvector. So principal component 1 comes from the first eigenvector, principal component 2 comes from the second one.
Thank you.
You're welcome. And they in the lab that they have you do by hand, and again, this is not super important if you're not interested in like the inner workings of PCA, but they talk about, I honestly off the top of my head forget how the sorting works, but the sorting of the eigenvectors basically makes it such that your first eigenvector will maintain the most variance in your data set. And I'll talk about that, I believe, in the next slide. But questions so far? All right, before we talk about that, I want to talk really quickly about how you use it in scikit-learn. I'm really just going to go off the documentation because I think that is enough. So typically, you only really need to use this n components parameter. So in this example down here, you just have like an x. And then here you can see they're instantiating PCA with 2 components. And the number of components is literally just the number of final columns that you want. You do a fit, and you can also do a fit transform, and you can do a transform. So actually, it works very, very similarly to your scalars, if that makes sense. So in terms of scikit-learn implementation, I just wanted to show that it works in a very, very similar way as your scalars or as your transformers or as your, actually like SMOTE also works in a very similar way. Your models has the .fit too. So I just wanted to show that. Questions about this? The solvers here, what's it here? Where's the SVD solver? All right, so SVD solver. Most of the time you wouldn't have to do this, But if you're curious as to what this is, SVD stands for singular value decomposition. It's actually something that we'll talk about on Friday with recommendation systems as well. But that is the process of breaking down your covariance matrix into the eigenvectors. So that's what the SVD is doing. And you very likely, I've not run into a situation where I have to change this up, but if you're curious, this is something that is, I would say, the second most used parameter here. Any other questions regarding the implementation? I will say that the lab for these are actually pretty good to go through. All right. So,
Excuse
question?
me, I have another question.
No, no worries.
In the diagonal of the correlation matrix, we have the same feature, right? And
Yes.
what about those?
Those are also taken into account. So those you don't have to worry about at all. It's just part of the nature of the matrix. It knows that the diagonal will be 1.
Okay.
Nice. All right. So something that people are always, I guess, a question that you should be thinking about. What's the best number of principal components? Right. So if your purpose of doing PCA is really to lower the dimensionality of data, if it's not for visualizations, because that really restricts you to 2D or 3D, or if you're not restricted by, the number of inputs that your model wants to take in, then you might ask yourself, okay, how many principal components should I keep? Now, PCA and your principal components are created with the idea of maintaining as much variance as possible. And sorry, what was I getting to? And you want to maintain as much variance as possible. And your principal components are also sorted. That's what I was looking for. They're also sorted by, no, this is where it is. And they're also sorted by how much variance they maintain. And so if you were to take all of your different principal components and plot them out, you can actually pull out an explained variance attribute. So one of the attributes out of PCA, and if we scroll down a little bit here, you can take a look at your explained variance. And it shows you the amount of variance explained by each of your components. So if you're trying to decide how many principal components should I keep, this is an example of a graph. I should have this labeled. And actually, let me just annotate this super quick. This would be proportion of explained variance. And then this at the bottom would be number of components. All right. So basically, you can imagine this is probably a data set with like 65 features. And you're just trying to figure out, all right, what's the number of features I want to pick? So you want to really maintain your variance as much as possible. Here you can sort of see it plateaus off. So you might say, all right, at somewhere around like 47 or 48, I actually still have almost 100% of my variance. And that's something that you can do. But you might also say, like, going down from 60 to 48, it's not a huge decrease. So it really depends on your scenario. Are you really trying to, maximize the runtime of your model? If you're really wanting to do that, maybe you can test several different number of principal components. You can see here at 30, you're still at roughly like, 95% of your explained variance. If you want just like 80% of your explained variance, that's like done at around like 13 principal components. So it really depends on what you're striving to do with your PCA. Explained variance, really you can see that with your first couple of principal components, you already have, let's say with 5 components, you already have like half of your explained variance. Really up to you to tune. This is going to be a very, very similar shape that you're going to see no matter what data set you're doing PCA on. But yeah, any questions? All right, again, PCA is not a project that you will do. PCA is very complementary. Most people do it for things like image compression, which is the last couple of labs that we saw over here. These, down here, and let me just clear this real quick. Here you can see this is on image processing, because in image processing, you imagine each pixel becomes a column. So that's why PCA is often used for that. PCA is also often used for NLP sometimes because NLP, every word becomes a column. And yeah, that's PCA. Any questions? That, I believe, was the last slide. Cool. The inner workings of PCA, very, very rooted in linear algebra. I think that's something that's important to point out. If you're ever asked about it, you can talk about linear algebra. You can talk about decomposition of your correlation matrix. But
I have a
yeah.
question in general. I think with PCA, so it's not, is it just a method to transform your data, or is it like a algorithm in itself? Because they kind of talk about it sometimes like it's like its own like standalone algorithm, I guess. So I don't really understand
Like where in the
yeah.
So it's the algorithm is already, so you can think of it is an algorithm just because there are a certain number of steps that will get from your original data set to your PCA data set.
Okay.
It's not a model. It's not a model just because it doesn't you're not really training anything. It's like set formula. So yeah, it's not a model, but it is an algorithm just because it has like a series of steps that you break down the correlation matrix, and then you just get your eigenvectors multiplied by your components. So yeah, I don't know if that was helpful.
For dimensionality reduction, and then you would on top of that apply another like a model to the data set.
Yeah, that's right. It's you can actually use, PCA is an intermediate step before your modeling. You can actually also implement it in your pipeline. If anyone had used scikit-learn's pipelines, you can actually use it as a step in your pipeline to maybe before or after SMOTE, before you use your model. You can use PCA then.
Okay.
Anything else? Cool. Very, very similarly, tomorrow's material on clustering will also, again, be something that is a complement to some of the projects that you will do. These both PCA and clustering can also be used complementarily as complements to your classification project. So if any of you decide to go back and work on your classification project, maybe you want to implement PCA if your models were taking a very long time to run. But keep in mind that with PCA and with dimensionality reduction, you are losing some data. Like, for example, you see here, if I did it down to 30, I'm losing 5% of the variance in my data. So usually your models don't perform better, just a lot more efficient. I think that's also something that's important to remember. Any final questions before I close out? Awesome. Well, really, really good job with the presentations today. I will see you all at your project reviews, and please submit your project. I think I still only have 2/3 of the class submitted. So please get that done. If you're having trouble, let me know. Just a reminder, you have to submit it in 2 places. So let me show you real quick. You have to submit it both in the phase 3 project and also in the GitHub URL. And of course, your blog post. But I think a lot of you, I haven't seen too many from here. I think, here I only have 14 out of 20 something of you. So don't forget here, this is not the student view, but there will be a submit assignment button there, and you'll upload the PDFs of your notebook, your slides, your README. So please remember to do that. All right, well, I have nothing else for you today. I'll see you all tomorrow for clustering. And have a good rest of your day, everybody. Really good job on the presentations. Bye.